Hello everyone, my name is Mohit Gupta and I welcome you to my YouTube channel Chem Fundamentals. In today's video we are going to discuss the gaseous state. This is part 1 of the series and rest of the parts would be updated soon. In this video we are going to discuss different gas laws, for example Boyle's law, Charles law, Gay-Lussac law and Avogadro's law. And one more important thing, the link of the PDF is available in the description box so you can go and download from there. So without further delay, let's get started. So first let's start with the general properties of gaseous state. It is the third state of matter where molecules or atoms are widely separated. And why it is so? It is due to the large intermolecular distance and low intermolecular forces. And this large intermolecular distance and low intermolecular forces develop several characteristics of the gases. For example, shape and volume. They neither have definite shape nor definite volume due to their large intermolecular distance. The density is also very low. It is lesser than solid and liquids but much higher than plasma. Next is compressibility. So gaseous states are very much compressible. If you exert some pressure onto them, they'll get compressed easily. Why? Because they have large intermolecular distance, so they can come closer to each other on applying pressure. So they are highly compressible. The next is diffusibility. It is the ability to get diffuse. So gaseous states have very high diffusibility. They can move from high concentration to the lower concentration with very high speed. Why? Because of low intermolecular forces. So they intermix with all the gases in all the possible proportions. The next is pressure. Since the molecules moves randomly in all the possible directions, therefore they exert equal pressure in all the possible directions. So next is amount of gas. How can we measure amount of gas? We can measure the amount of gas in terms of moles or grams. For moles, the formula for moles is already known. It is equals to the mass of the gas divided by its molar mass. Next is volume of gas. Volume of gas can be measured in terms of liter, in terms of meter cube or centimeter cube. So it is generally expressed in liter or meter cube. But since they are large quantities, so for the smaller quantities, we generally use centimeter cube, decimeter cubes. And for that, you should know 1 meter is equals to 10 decimeter, which is equals to 100 centimeter. And after that, you have to remember that 1 ml is equals to 1 centimeter cube and 1 liter is equals to 1 decimeter cube. If you know these two conversions, you can easily convert one unit into the other. So here in this case, I have written 1 liter is equals to 1 decimeter cube. And how many meter cubes it would have? 1 decimeter is equals to 10 to the power minus 1 meter. That means if I cube it, I'll get 10 to the power minus 3 meter cube. After that, in terms of centimeter, it would be 10 to the power 3 centimeter. How come? We know 10 decimeter is equals to 100 centimeter, which means 1 decimeter is equals to 10 centimeter, and if I'll cube it, I'll get 10 to the power 3 centimeter cube. This is cube. From here, 1 meter cube is equals to 10 to the power 3 decimeter cube, and if I'll cube this, I'll get 10 to the power 6 centimeter cube. If you know the conversion of 1 meter into decimeter and centimeter, you can easily play with all these units. The next is pressure of gas. The pressure of a gas can be measured in terms of atm, bar, mm of Hg, torr, pascal, etc. And here the conversion of unit is also very important. 1 atm is equals to 760 mm of Hg, because at 1 atm the height of the mercury is 760 millimeters. 760 mm is equals to 76 centimeter, and which is also equal to the 760 torr. We don't use torr nowadays, however in some questions you will find written torr. This is also an important conversion where 1 atm is equals to 1.01325 bar. You have to remember all the digits here. And 1 bar is equals to 0.987 atm. If you divide 1 divided by 1.01325, but you will get 0.987, and it is very easy to remember, 0.987. The next is 1 pascal is equals to 1 newton per meter square, and which is equals to 1 kg per meter per second square. So these are the kind of dimensions, and you can easily find it out using the formulas. Next is 1 atm is equals to 101.325 pascal. You can see here 101.325 and 101.325. Actually 1 atm is equals to 101,325 bars, and 1 bar is equal to 10 to the power 5 Pascal. So if I have to convert atm into Pascal, I have to multiply by 10 to the power 5 Pascal. In that case, I'll get 1 atm is equals to 101,325 Pascal. You can easily interchange these units if you know the relation between atm, bar, pascals. Okay. So now to measure atmospheric pressure, we generally use barometer, and to measure the pressure of any gas, we generally use manometer. So what is barometer? Barometer is a glass equipment. You can see here we have taken a glass tub here, and above which we have suspended a column. In this case, we have taken mercury. So atmospheric pressure is the pressure which is exerted by the atmosphere. So atmosphere exerts some pressure over here and the mercury rise in the column. So this is the height of the mercury which is equal to the 76 centimeter or 760 mm. That's why we called 1 atm is equals to 760 mm of Hg. But point to be remember here that it is at 0 degrees Celsius, which is equals to 273 Kelvin. This is the standard condition at which we measure the atmospheric pressure. Now, what is the use of using mercury here? So mercury is having very high density, and moreover we know that the height of the column is always inversely proportional to the density. So we can use a smaller column to prepare this barometer. The next important thing is mercury doesn't stick to the glass, therefore it is appropriate for us. Moreover, it is non-volatile at room temperature, hence it has negligible vapor pressure. Since it is non-volatile, its mass would be constant and it won't change during this measurement. Now, if I know the height of this column and if I know the density of the mercury, then how can I find out what is the atmospheric pressure? In that case, I have to use the formula pressure is equals to force per unit area, and force is equals to mass into acceleration. Now, what kind of acceleration are we having in this measurement? The acceleration is acceleration due to the gravity. So we are going to use the gravity here. In order to find out the mass, we have to know the volume or the density. Since the density of mercury is available in literature, we can easily use it at 0 degrees Celsius. Now, mass would be equal to density into the volume. Now, in order to find out volume, we have to take the area of cross section of this column as well as the height. So in that case, I have taken A as the area of cross section and H to be the height. So the volume of mercury would be area into height, that would be equal to A centimeter squares into H centimeter, which come out to be AH centimeter cube. On rearranging, I have seen mass is equals to density into the volume. So I'll substitute this value. What I'll get rho AH grams. What is rho here? Rho is the density of the mercury, and the volume is AH centimeter cube. The unit of density is gram per centimeter cube. So centimeter cube will be cancelled out by the centimeter cube and we're left with the gram. So the unit of mass is in the grams. The next is we'll substitute the value of mass and the acceleration in the formula of force. What we'll get? A H rho into G. The unit of the force is gram meter per second square because the unit of gravity is meter per second square and the unit of mass is gram. So what we'll get? Gram meter per second square. Now the pressure is force per unit area. If I'll substitute the value of force here, what I'll get? Rho A H G divided by A. Since A is also the area of cross section, so on division what we'll get? We'll get rho G H, and the unit of pressure would be gram per meter per second square. So now the pressure exerted by the mercury column of exactly 76 centimeter at 0 degrees Celsius at sea level would be considered at standard atmospheric pressure, which is equals to 1 atm. So at 1 atm, the height of the mercury is 76 centimeter or 760 mm. To measure the pressure of different gases, we use manometer. We generally have two kind of manometer, a closed limb or an open limb. The next is temperature of gas. So we can measure the temperature of gas in terms of Kelvin or on the degree Celsius scale. And we also know the conversion factor. Kelvin is equals to degree Celsius plus 273.15. So we have to add this factor into the degree Celsius. To measure temperature, we generally use thermometer, and thermometers are generally equipped with mercury. And why we use mercury? First of all, mercury being liquid, it doesn't stick to the glass, obviously. Moreover, it has very high expansion coefficient, which means it is extremely sensitive to the temperature and it can expand sufficiently enough even at small temperature change. So if the change is of 0.1 degrees Celsius, the mercury would expand sufficient enough that we can easily measure the difference in the height or difference in the mass. So next is Boyle's law. The Boyle's law was introduced by the Robert Boyle in 1662. He carried out an experiment to define the effect of pressure onto the volume. So according to him, the volume of a given mass of a gas is inversely proportional to the pressure at constant temperature. So we have two important things. The mass of the gas should be constant. We should not introduce more or we should not remove the amount. So which means we have to take a constant mass of the gas. The number of moles should be constant. Along with that, it should have constant temperature. Only then this formula would be followed. According to him, the volume is inversely proportional to the gas. So if I increase the volume, the pressure would decrease, or if I increase the pressure, the volume would decrease. Now, if I have to remove this proportionality constant, I have to write the equal to and I have to introduce a constant here, which is K here. So in this case, if I'll cross multiply here, what I'll get, Vp is equals to K, where K is the constant. Now at two different temperature, at temperature T1 I can write P1 V1 is equals to K. At temperature T2 I can write P2 V2 is equals to K. Since the constant have the same value, we can easily write P1 V1 is equals to P2 V2. Or we can even divide these two equations. What we'll get the same result. So let's talk about the isotherm. What is isotherm? It is the plot of pressure versus volume at constant temperature. So whenever we have a constant temperature and we plot a graph, that would be considered as isotherm. In this case, I have taken pressure on y-axis and I have taken 1 by v on the x-axis. Since pressure is directly proportional to the 1 by v, in that case the graph will go in a straight direction and it will pass through the origin. In the other case, I have taken P is inversely proportional to V. So here I am plotting volume on x-axis and pressure on the y-axis. In that case, I'll get this kind of graph. Here in this case, we can see at low volume the pressure would be high, and at high volume, the pressure would be very low. This line moves parallelly to the y-axis at very high pressure, and this line also moves parallelly to the volume at very large volumes. Now, on plotting the graph between P and 1 by V at different temperature, what I'll get three lines, three or more lines, depending upon how many observations I have taken. So in this case, we can say all these lines are passing through the origin. I have written T3, T2, T1, but I don't know which temperature is higher than which one. So in this case, let's take an example. If I'll make an imaginary line like this, then the value of pressure would be higher for T3, then T2, and then T1. So we know on increasing temperature, the gas expands, and on expansion, it would have larger pressure. In that case, at higher temperature, the pressure would be higher. So T3 is greater than T2, which is greater than T1. Moving further, if I'll make this graph at different temperature, I'll get T1, T2, T3. So if I'll draw a line, imaginary line like this, then the volume for T1 is lesser, volume of T2 is more, and volume of T3 is even larger. At higher temperature, gas expands and hence it has larger volume. This means that T3 is greater than T2, which is greater than T1. And if I will plot a graph between PV and V, in that case, what will I get? I'll get a straight line. Why? Because if I'll increase P, the volume would decrease and the product of this is constant. So next is the significance. What is the significance of this law? It signifies that gases are compressible. Higher is the pressure we apply, the denser it will become. So let us find out what is the relation between the density and the pressure. So density is mass per unit volume, where I have taken W for the mass and capital V for the volume. Rho is already density. On rearranging, what I'll get, volume is equals to mass per unit density. Now we know PV is equals to constant. So if I'll substitute the value of V, what I'll get P into W divided by rho is also constant. On further rearranging, what I'll get, Pw is equals to rho into K. Since I have taken a constant mass of a gas, moreover, the K is also constant, which directly means pressure is directly proportional to the density. So higher is the pressure we apply, the larger would be the density of the gas. Next, we come to an important question: why it is difficult to breathe at high altitudes? So at high altitudes, the atmospheric pressure is low. So if the pressure is low, the density would also be lesser. In that case, a lesser amount of oxygen would be available in a larger volume, and we have to take air in very high quantities to meet our oxygen requirements. The next is, while inflating a balloon, the volume and the pressure of the gas increases simultaneously. Why? According to this Boyle's law, pressure is inversely proportional to the volume. However, in this case, the pressure is directly proportional to the volume as both are increasing simultaneously. So how we can justify this? So one important thing we have to note here, that we are inflating a balloon, which means we are introducing the matter into the balloon. Hence, we are increasing the mass of the gas. However, the Boyle's law is applicable at constant mass. This means the Boyle's law is not applicable here. It is only applicable if we keep the amount of the gas constant. The next is Charles' law. The Jacques Charles in 1987 carried out this experiment to find out what is the effect of temperature onto the volume. So according to him, the volume of a given mass of the gas, we have again taken as constant mass, is inversely proportional to the temperature in degree Kelvin at constant pressure. So we have to keep the pressure constant, we have to keep the mass of the gas constant, and on degree Kelvin scale, the volume is inversely proportional to the temperature. Till at degree Celsius case, Vt is equals to V naught plus V naught by 273 into T. Since it is at degree Celsius scale, we have to introduce the factor of 273, where V naught is the volume of the gas at 0 degrees Celsius, which means we have taken the standard condition. T is the temperature of the gas and Vt is the volume of a gas at temperature T. Now Vt is equals to V naught. I have taken V naught common, but I'll get 1 plus T by 273. Now from this formula I can easily say that the volume of a gas increases or decreases by a factor of 1 by 273 to the volume of 0 degrees Celsius for every 1 degree change in temperature. Which means if I'll take the value of temperature as 1, in that case the volume would increase by a factor of 1 by 273 to its original volume. So at 1 degree Celsius, I have to write down the T as 1. I'll get this. At minus 20 degrees Celsius, what I'll get, Vt is equals to V naught minus 20 V naught by 273. And at 273 degrees Celsius, what I'll get, 273 V naught. In this case, 273 will be cancelled out by 273, and what I'll get, V naught minus V naught, which is equals to 0. Hence, the volume of gas at minus 273 is equals to the 0, which suggests gases at minus 273 Kelvin has zero volume, that is, they don't exist at this temperature. Okay, so in reality, all the gases liquefy before reaching to minus 273 degrees Celsius or 0 Kelvin. It is important to note here that minus 273 or 0 Kelvin is a hypothetical temperature, extremely difficult to achieve. Now if I'll make this graph on degrees Celsius, I have taken volume on y-axis and temperature on x-axis. I'll get a straight line because they are directly proportional. But on degrees Celsius, we have a intercept of this much. On extrapolating, the line would merge at minus 273 degrees Celsius, and this point the volume would be 0. Since the pressure is constant, we call this graph as isobar. So what is absolute zero? It is the lowest possible temperature where all the gases are supposed to have zero volume. Moreover, it is also a hypothetical temperature. So if I'll make this graph, the volume versus temperature at different pressures, but I'll get all these four lines and they all are merging at minus 273 degrees Celsius. However, it is more cleaner at Kelvin scale. Here I have taken temperature in Kelvin. In this case, all the lines are merging at 0 Kelvin at origin. So now let's talk about the relation between K and degree Celsius. So K is equals to 273 plus degree Celsius. We already know this. So I can write T in Kelvin is equals to 273 plus temperature in degree Celsius. So in that case, Vt is equals to V naught 273 plus T divided by 273. This was our formula. We have seen it before. Now 273 plus T can be written as capital T. What we'll get on substitution, we will get Vt is equals to V naught T by 273. Now 273 is a constant and V naught is the volume at 0 degrees Celsius, which is also constant. This suggests that volume is directly proportional to the temperature. So we can write it down as V is equals to Kt, or V by T is equals to K, which is a constant. At two different temperature, I can write V1 is equals to Kt1 or V2 is equals to Kt2. On dividing these two equations, what I'll get, V1 upon V2 is equals to T1 by T2, or I can even cross multiply. What I'll get, V1 T1 is equals to V2 T2. So these are the few expressions which we can easily derive from V is equals to Kt. So this relationship is only valid at constant pressure and for a given amount of gas. Next is significance. So what is the significance? It means that gas expands on heating and results in lower density, which in turn suggests that hotter air is lighter than the common air, and we can use hot air balloons to rise up in the sky. The next is Gay-Lussac law. So he generalized the relation between temperature and pressure, but at constant volume for a given amount of a gas. So the amount of gas is also constant. According to him, the pressure of a given mass of a gas is inversely proportional to the temperature in degree Kelvin at constant volume. Mass is constant, volume is constant, and the pressure is inversely proportional to the temperature, but at Kelvin scale, not at degree scale. Now we can easily write down at degree Celsius scale, Pt is equals to P naught plus P naught divided by 273 into T, where P naught is the pressure at 0 degrees Celsius, T is the temperature, and Pt is the pressure at temperature T. T is the temperature at degree Celsius. On taking P naught as common, what I'll get, 1 plus T by 273. And if I place temperature as 1 degree, then the pressure of the gas would vary by a factor of 1 by 273 with respect to the P naught. Now I can take LCM, what I'll get, 273 plus T, and now T plus 273, where T is in degree Celsius, so it will become in the Kelvin. Now I can write down capital T. Since P naught and 273 both are constant, therefore P is directly proportional to the temperature. On removing the sign of proportionality, I can write P is equals to Kt, where K is the constant, or I can even write it down as P divided by K is equals to constant. At two different volume, P1 is equals to Kt1 and P2 is equals to Kt2. On dividing the two, what I'll get, P1 by T1 is equals to P2 by T2 at constant volume. Now if I'll make a graph between pressure and temperature, I have taken temperature on x-axis and pressure on y-axis. In that case, this graph is known as isochord because it is at constant volume. I have taken four different volumes and all are passing through the origin. The next is Avogadro's law. According to Avogadro's law, same volume of all gases contains same number of molecules at constant temperature and pressure. So if you take the temperature and pressure constant, in that case, all the different gases having the same volume would contain same number of molecules. So here you have taken the same volume. So we know 1 mole is equals to 6.022 into 10 to the power 23, and if I'll take 1 mole of different gases and all of them having same temperature and same pressure, then we would have the same volume. Now the volume is directly proportional to the number of moles. Higher is the number of moles, higher would be the matter, and higher would the volume it would occupy. Now we can write down V is equals to K into N. The K is constant here and N is the number of moles. So number of moles can be defined as the mass of the solute divided by its molar mass. So I can write M divided by capital M, where M is the mass of the gas and capital M is the molar mass. Now if I'll rearrange, but I'll get M is equals to K small m divided by V. Mass per unit volume is your density, so I can replace it with the rho. Now we can write it down like M is equals to K into rho. Hence, I can say the density is proportional to the molar mass of the gases. Higher is the molar mass of the gases, higher would be density. Hence, to make the number of moles constant and to make the volume constant, the molar mass and density changes with each other. If the gas having higher molar mass, it means it has higher density. If a gas is lower molar mass, then it means it has lower density. Hence, the volume of all the gases remain constant. Okay. Now, we know one more important thing. Vapor density is the density of the gases divided by the density of hydrogen. We have taken hydrogen as a standard, which means the vapor density is the density of gas with respect to the density of the hydrogen. In this case, if I'll take the volume of the two gases same, which means vapor density would be equal to the mass of the gas divided by the mass of hydrogen. Since density is mass per unit volume, so volume would be divided by the volume. Now the total mass of the gas would be dependent upon the number of molecules. So if it has n number of molecule and the mass of one molecule is something, then we can write the total mass is equals to n into the mass of one molecule, where n is the number of molecules. So I can write down like mass of n molecule of gas divided by mass of n molecule of H2 gas. Now if I'll assume one molecule of the gas, so n is equals to 1. In that case, mass of one molecule of gas divided by mass of one molecule of H2 gas. So mass of one molecule of gas, mass of one molecule is equal to the molar mass. So I can easily write vapor density is equals to molecular mass of the gas divided by molecular mass of hydrogen gas. And what is the molecular mass of hydrogen gas? It is 2 units or 2 grams. So in that case, vapor density is equals to molecular mass of the gas divided by 2. Hence I can say the molecular mass of the gas is twice the vapor density. So m is equals to twice of rho. So this is an important formula which we use in several numericals. Now along with that, vapor density is equals to mass of gas divided by mass of hydrogen. I have taken it from the here. This means molar mass is equals to twice into the vapor density, which means twice into the mass of the gas divided by mass of the hydrogen. Now if I'll take 1 liter of a simple gas and 1 liter of hydrogen gas, in that case I can write it down. Molar mass is equals to 2 into the mass of 1 liter of gas divided by mass of 1 liter of hydrogen gas. So mass of 1 liter of hydrogen gas is 0.089. This is an experimental value. So I can easily write mass is equals to 2 into mass of 1 liter gas divided by 0.08. So if I'll divide 2 divided by 0.089, what I'll get? 22.4. So the molar mass is equals to 22.4 into the mass of 1 liter of gas. And these all the calculations are carrying out at standard temperature and pressure. Temperature should be 0 degrees Celsius or 273 Kelvin, and the pressure should be 1 atm. So hence I can write down molecular mass is equals to mass of 22.4 liter of a gas at STP. Okay, so whatever is the mass of the gas is at 22.4 liter, it would be equal to the molecular mass. Hence I can write 22.4 liter of any gas at STP is equals to its molecular mass, and this is also known as gram molecular volume. So at STP, which is standard temperature and pressure, that is equals to 273.15 Kelvin and 1 atm, the molar volume is 22.4 liter. However, if I take pressure in 1 bar, then the value becomes 22.7 liter. And at the end, if I take pressure in 10 to the power 5 Pascal, exact value, then I'll get 22.8 liter. Actually, 1 bar is equals to 10 to the power 5 Pascal. However, the value differs in decimals, and on rounding off, what I'll end up to 22.8 liter of volume. So we reached to the last question, which is what is the volume of N2 gas and AR gas, argon gas at 273.15 Kelvin and 1 atm. So these are the standard conditions here, and the volume, molar volume is 22.4 liter. So under this STP condition, all the gases have the same volume, which is equals to 22.4 liter if we have 1 mole of each gas. So what we have studied so far, we have talked about the general properties of gaseous state. We have talked about the Boyle's law, Charles' law, Gay-Lussac law, and Avogadro's law. So this is it for the today's video. If you like the video, then please hit the like button, and if you are new here, then please consider subscribing. So this is Mohit Gupta signing off. Have a great day.